Physics insists that the universe cares nothing for past or future. Its deepest laws treat time as a directionless dimension, yet we feel each moment slip away. In 1928, a quiet mind in Bristol wrote an equation that predicted antimatter. He would later earn a Nobel Prize. Why does time ache for us, but not for the cosmos? The answer begins with Paul Dirac. Paul Dirac was born in Bristol, England in 1902. His father, Charles, was a stern language teacher who enforced a strict rule at home, French only at the dinner table. Conversations became exercises in precision, and mistakes meant silence. The atmosphere was tense, measured, and often lonely. Dirac's childhood, described by biographers as desperately unhappy, left him withdrawn, speaking little, and seeking refuge in the clarity of numbers and lines. He began with engineering at the University of Bristol, mastering technical drawing and projective geometry. Mathematics soon called to him, offering a world where logic replaced uncertainty. In his notebooks, equations stood in for words. By 1923, Dirac arrived at Cambridge, entering a community that valued eccentricity and brilliance in equal measure. He kept to routines, walked the same paths, and wrote home on postcards that spoke only of the weather. Long silences became his signature, both in conversation and in lectures. In the late 1920s, quantum theory was struggling to keep pace with the new realities of the atom. Existing equations could not explain the electron's behavior at speeds near that of light. Dirac, working alone in his small Cambridge room, set out to find a formula that would respect both quantum mechanics and Einstein's special relativity. He wanted an equation that would not break the symmetry of space and time. In 1928, Dirac wrote the equation I gamma mu partial mu minus m psi equals 0. The Dirac equation was the first to unite quantum mechanics with relativity, describing the electron as a wave in space-time. The equation's structure demanded 4 components, a spinor field, and introduced new mathematical objects called gamma matrices. It predicted the electron's spin and magnetic moment with uncanny accuracy. But the mathematics insisted on something stranger, solutions that implied the existence of particles with the same mass as the electron, but opposite charge. Dirac's paper, published in the Proceedings of the Royal Society, quietly set the stage for a new chapter in physics. The world had not yet seen antimatter, but the mathematics left no room for doubt. In the silence of his Cambridge study, Dirac had written an equation that looked both forward and backward in time, indifferent to direction, indifferent to the hopes and fears of those who read it. It is a quiet, unresolved thought. The fundamental laws, written without preference, behave the same toward past and future, and yet our experience does not. The question lingers at the border between elegant mathematics and the lived flow of time. In 1932, a thin arc of silver nitrate revealed what Dirac's mathematics had already written. Carl Anderson at Caltech watched a single track curve through a cloud chamber, evidence of a particle with the mass of an electron and a positive charge. The positron, predicted by the Dirac equation in 1928, had become a fact of the world. Nature had answered an abstract question with a visible mark. Skepticism in the physics community gave way to quiet awe. The negative energy solutions, once dismissed as a mathematical inconvenience, now described a real particle that no one had imagined before Dirac's equation made it inevitable. Recognition followed swiftly. In 1933, Dirac shared the Nobel Prize in Physics with Erwin Schrödinger. The citation spoke of new productive forms of atomic theory. But for Dirac, The deepest satisfaction came not from prizes or public acclaim, but from the structure of the equations themselves. He would later write, "It is more important to have beauty in one's equations than to have them fit experiment." To Dirac, mathematical beauty was not a luxury, it was a signpost, a compass pointing toward truth. He trusted beauty as a guide, even when evidence lagged behind. The Dirac equation, with its symmetry between matter and antimatter, had found its place in the world. In the silence that followed, the meaning of time and symmetry began to press more deeply on physics. Dirac's pursuit of beauty had opened a path, but the question of time, its direction, its meaning, remained unresolved, waiting at the edge of the equations. At the most fundamental level, the equations that describe nature are silent on the direction of time. Newton's laws, Maxwell's equations, and the Dirac equation itself remain unchanged if the arrow on the clock is reversed. Replace time t with minus t, adjust momentum and spin, and the mathematics continues its work, indifferent to which way the film runs. This symmetry is not a quirk, but a deep feature of the rules that govern particles and fields. The equations do not care about memory or regret. They do not know about before and after. Yet, in the world of experience, time is not a loop or a mirror. It is a river that flows in one direction only. A cup shatters but never reassembles. Smoke drifts away from the match and never returns. This contradiction between the time symmetry of the laws and the irreversibility of daily life has troubled physicists for generations. The answer lies in the concept of entropy. In the late 19th century, Ludwig Boltzmann showed that entropy measures disorder, or the number of possible microscopic arrangements in a system. The second law of thermodynamics states that for an isolated system, entropy tends not to decrease. A drop of ink in water will spread and mix, never spontaneously gathering itself back together. The direction of time, as it is lived, is the direction in which entropy increases. Arthur Eddington called this the arrow of time. It is not written into the equations themselves, but emerges statistically from the overwhelming likelihood that disorder will grow. The universe began in a state of low entropy, and since then, every moment has carried it further from that improbable starting point. The arrow is not a law, but a tendency, one that shapes memory, decay, and the feeling that the past is fixed while the future remains open. At the level of atoms and particles, nothing forbids time from running backward. But in the world of broken cups and fading photographs, the arrow persists. The laws remain symmetric. The universe, in its indifference, lets entropy do the work of choosing a direction. In the end, we are left with a quiet, unresolved tension. The rules that govern particles and fields do not distinguish past from future, and yet the life we live points one way. Memory holds the past. Decay points toward what has been. The mathematics stands apart, impersonal, and time, as we feel it, keeps its patient insistence. Einstein's relativity shattered the idea of a single universal time. Clocks on speeding trains or perched atop mountains drift apart, each marking its own rhythm. What one observer calls now, another might call history. Space-time itself bends and warps, unmoved by the lives passing through it. Dirac's equations grew from this landscape, demanding that quantum laws honor the relativity of time. For him, the electron was not a particle ticking to one master clock, but a ripple in space-time, its fate tied to shifting coordinates. Yet quantum mechanics draws a line. Time in this theory is not an operator, never something to be measured or manipulated, just a parameter, a silent label for the order of events. Wolfgang Pauli challenged this, asking why time should be different from position or momentum. The answer, hidden in the mathematics, is that making time an operator would break the theory's fragile structure and lead to contradictions with energy. Dirac accepted this boundary, but it left a gap, a place where knowledge ends and assumption begins. In 1937, Dirac looked beyond equations to the universe itself. He noticed that certain numbers, the ratio of gravity's strength to electricity, the age of the cosmos in atomic units, are all immense, 10 to the power of 40. He wondered if these were not coincidences, but hints that nature's constants might drift as the universe ages. His large numbers hypothesis was a leap, suggesting cosmic time could shape the laws of matter. Later experiments found no evidence for changing gravity, and the idea faded. But Dirac's willingness to follow mathematical whispers, even when they defied common sense, marked his career. Dirac rarely spoke. His lectures were long stretches of silence, as if words risked disturbing the balance he sought. He spent decades searching for a theory that would unite quantum mechanics and Einstein's curved space-time, a quantum gravity where time would be woven into the fabric, not left outside. The search goes on. No framework has bridged the gap or explained how time's arrow emerges from laws that see no direction. Physics stands between two worlds. In the math, time is relative and reversible. In life, it moves forward, never back. Dirac's work lingers at that boundary where beauty and mystery refuse to resolve. Modern physics still offers no complete theory of time. Its direction remains an emergent puzzle, not a settled fact. As our equations grow more precise, the mystery lingers. Every second, we move forward, even as nature's laws remain silent. Time's true nature is unfinished, and so is our understanding.